Now, the instantaneous velocity problem goes more or less like this. Imagine that you throw a football vertically upwards from the ground with an initial speed of 96 feet per second. So the situation is like this. Someone's standing up like that on the ground, and they throw a football up. So they throw it up. Football's going to certainly travel upward, then fall again, right? So that's going to happen. And from physics, if you use the acceleration of gravity, the fact that the velocity changes over time, all the equations that you already know from physics, you're going to see that this is an equation that measures the height of the football, where t is the time after the ball is thrown, okay? So how do we find the average velocity of the football between t equals 1 and t equals 3? So we do that by saying the average velocity will be the change in distance, the change in space over the change in time. So that will be s of 3 minus s of 1 over 3 minus 1. So that will be, so plug 3 into the equation. So that's minus 16 times 9, plug in 3, plus 96 times 3, minus, and then s of 1 is what you're going to plug in. So that will be minus 16 times 1 squared, plus 96 times 1, all of that divided by 3 minus 1, which is 2. So I'll do the math here with my faithful calculator, and I'll get a 32 feet per second. So what I'm saying is, between t equals 1 and t equals 3, the average velocity of the football is 32 feet per second. So this means to say that if the football had kept constant velocity throughout these 2 seconds from t equals 1 to t equals 3, that constant velocity of 32 would take it to the same place that its actual velocity took it, right? That's what the average velocity is about. Now B. Same thing, but now with t equals 1 and t equals 2. So we're doing s of 2 minus s of 1 over 2 minus 1. So that will be minus 16, 2 squared, plus 96 times 2, all that divided 2 times 1, right, which is 2. So I use my calculator for that. Just checking on my calculator my result here, and that gives me a 48 feet per second. So that's the average velocity on this new interval. So as you change the interval, of course, the average velocity changes. Same idea. If the ball had kept a constant velocity throughout this 1 second from t equals 1 to t equals 2, that would take me, so that constant velocity of 48, would take the ball to the same place that its actual velocity took it, right? Now note again that the velocity is not constant. This is an important thing to notice. So it starts with a velocity of 96 positive going up, but for example, it slows down, and it stops at the very height, at the very peak of the trajectory, and then the velocity starts to increase again as it starts to fall faster and faster and hits the ground. Okay? So the velocity is never constant, but the average velocity kind of pretends that it's constant to allow for the calculation. So everybody knows how to calculate average velocity, but what if I wanted to know the exact velocity of the ball, say at t equals to 1? T equals to 1 second. So what if I wanted to know is what I'm saying. The instantaneous velocity. So 1 second after the ball is thrown, exactly 1 second after, not doing the time interval, but exactly at t equals 1, what is the velocity of the ball? That is my question. So I proceed like this. I took this time interval, which we're going to call delta t, or change in t, and I make it smaller and smaller. So I'm going to repeat the same problem, but now with t equals 1 and t equals 1.5, so that will be s of 1.5 minus s of 1 over 1.5 minus 1. So same thing as before, you plug in 1.5, just like you did here with 3. You plug in 1 just like you did here. I'll just do it directly with my calculator. That's going to be a 56. What if you make it even smaller, right? From t equals 1 to t equals 1.1 second. So just a tenth of a second of interval. It's very, very small, right? So same thing. S of 1.1 minus s of 1 over 1.1 minus 1. Same exact calculation, but now with 1.1 instead of 1.5. That gives me a 62.4 feet. Note how the change from 32 to 48, so I'm reducing the size of the interval. It was very big, right? We gained 12 feet per second, 16 feet per second from here. Now from 48 to 56, we gained 8 feet per second. Now here, we gained a lot less than that, right? We only gained 6.4 feet per second. What happens for the next interval? So s of 1.01 minus s of 1, all that divided by 1.01 minus 1. Again, checking with my calculator. That will give me a 63.84. So this is getting slower, right? This change is getting smaller and smaller and smaller. So what if I made it even smaller, right? What if I made it, let's say, t point, and that's the question, right? What if the time delta t was 0.001, meaning the interval were from t equals 1 to t equals 1.001, right? That would get even smaller, and the expectation is that this thing would stabilize around something. And the something that it stabilizes around is 64. As you can see, 63.84 is pretty close to 64. So this would allow us to guess the instantaneous velocity of the football at t equals 1 as 64 feet per second. Meaning, at that exact moment, at t equals 1, the ball is moving at 64 feet per second. We're not considering a time interval now. I'll put an approximation here just because we don't know, we haven't formalized how we calculate the exact value yet. But the idea is there, and I hope this was clear.